Alright, so here we have another video about converging lenses and how they form images. There's going to be one particular special case in this video, and that's the case of the magnifying lens and how exactly that works. It is a double convex or converging lens, as we've been talking about. So the glass is curved outward on both sides, and that's true for all thin converging lenses in any case. I'm sure most of you have seen a magnifying glass and you've seen what it does, but it only works in certain conditions. So we'll talk about that later in the video. First, we're going to talk about several specific scenarios that you can have with regard to where the object is as compared to the focal length, or another variable that we're going to call double the focal length. So point F and point 2F are interesting points when we're talking about images and objects and where they form relative to the lens. Alright, so let's go. So here's our first option. Option A is what I'm calling it. Option A is where the object is located further away from the lens than 2F. So 2F is just double the focal length. If you take the length from the lens to the principal focus and then double that, that's 2F. Alright, so the object is further away from the lens than 2F. Right? The basic features of the image that we're going to talk about here are true for any object location that is further away than 2F. It could be really, really, really far away. The basic principle is still the same. Alright, so let's look at what happens here. If we draw in two of our special rays, they're going to intersect right here on the, we did ray number 1 and ray number 2, if you remember from the previous video. So where they intersect is where the image forms, and then the intersection is the tip, and the base of the image is on the principal axis. So there you have it. Now notice what's true about this image. Number 1, it's upside down. Number 2, it's smaller than the object, right? So if we look at the object right here, and then the image, it's not super obvious, but it should be fairly clear to you that the image is smaller than the object, right? It's smaller than the object, it's inverted, it's upside down, right? Object is pointed up, image is pointed down. And it's what we would call real, but we'll get more into real and virtual later in this video. Alright, so those are the factors. It's inverted, it is real, and its size is diminished. The location of the image is between F and 2F. So it's going to be closer to the lens than 2F, but further than F. It will be between these two. Any distance the object is further than 2F, the image will be located somewhere in this vicinity, and it will be smaller than the object. Alright, that's case number 1. Option B is where you put the object between F, 2F, and F. Between F and 2F, the object. Any distance, any location of the object in between those 2 points will result in this scenario. Alright, so we draw in the ray number 1, bam, just like that. Ray number 2, straight through the middle. Where they intersect is over here. Draw in the image, and there we have it. It is further away from the lens than 2F, and it's larger, right? The size is bigger than the object was. So those are the features of option B. Alright, option B. If the object is located between 2F and F, like this, then the image will be further away than 2F, and it will be larger. So still inverted. So vocab terms for this: inverted, real, enlarged, it's bigger. And then where is it located? It's located further away than 2F. Alright. Okay, so here we have option C. This is the first, what I call a special case of a scenario where the object is located exactly at 2F, double the focal length. Alright, and something very interesting happens here. When we draw in our special rays, just like usual, and then we draw in the image, we notice something rather interesting. The object is located exactly at 2F, and the image is also exactly at 2F, and it's the same size. So only when the object is at double the focal length is the image the same size as the object, and in fact the same distance away from the lens. So this is interesting case number one, special case, the first special case, which I called option C. The features of the image are what I call vocab terms. It is inverted, it's real, same as the other ones, and the same size. All right, and where is it located? It is at 2f, but on the other side of the lens. Okay, that's option C. Now on to option D. This one is extremely interesting. All right, so here we have the object closer to the lens than f. And when we draw in our special rays, if you would ignore this part over here for the moment. So we draw in the special rays. So let's just zoom in on this part. So this one, ray number 1, and this one, ray number 2. What do you notice about them? I'm sure you've probably noticed this at this point. They do not intersect. They are separating away from each other. They are not going to ever intersect over in this area. They're diverging. They are not converging, those two rays. So there is going to be no image over here because there's no intersection of these two rays. So no image. Interesting. However, if you were to look at this lens from this side, so if you're looking from over here, I'll draw in an eye. Let me pause it while I do that. Okay, so I've drawn in a really poor looking eyeball, but in any case, that's to show that your observer is over on this side of the lens now. So you have to be looking from over here through the lens, and you will see something very interesting. You can follow the path of these light rays backwards. Alright, I guess technically I should have drawn this down here, but it's okay, you would still see the image from here as well. If you trace these rays backwards, they do intersect over on the side over here. They intersect. So if we draw in the image there, whoa, this is a totally different image. And in fact, this one can only be seen, this image can only be seen if you're looking at the lens from over here. All of the, well, let's go with that. So you can only see this image if you look through the lens from over here, and then you would see this image of the object, which is has some interesting features. It's different. All the other three cases, we said it was inverted and real. In this case, it's not inverted, it's upright, same as the object. It is not real, it is virtual, and it's larger than the object. All right. It's also going to be further away than f from the lens, on the same side, and you have to look at it from the opposite side, otherwise you cannot see this image. That is why it's virtual. All right. These light rays that I drew, these light rays, they do not actually pass through the location of the image, right? The ray starts here and it goes there and it keeps going. It does not actually go backwards. But if you were to look at it from over here, it would appear as though it came from there, right? It looks like it came from up here, but it did not actually come from up there. No light that you're looking at ever came from this location. That's why it's called a virtual image. There is no light that comes from the image to your eyes, right? If we were to go back to the other examples, you would be able to see that in all of those cases, the light rays, the actual light rays pass through the location of the image, right? And that means that it's a real image. You can project those images onto a screen. This image you could not project onto a screen. You can only see it if you look at it from here, and that's why it's called virtual. All right, so what do we call option D? It's a magnifying lens. It provides an enlarged image of the object. It's, as I was just saying, the image is not real, it's virtual. None of the light rays that actually enter our eye from the object pass through the location of the image. So none of those light rays that we see actually came from the location where the image appears to be, right? They came from a different location, which is where the object is. The image that we see is not the same thing as the object. Well, you just saw the drawing of it. So anyway, A virtual image is an image that the light rays do not actually pass through the location where the image is. In addition, a virtual image requires you to be at a specific perspective in order to see it. So that's the difference between real and virtual. A real image has light rays that pass through the actual location where the image forms and then enter your eye. A virtual image does not have any light rays that enter your eye and also pass through the same location where the image forms. Alright, I hope that was clear. I know this video was a little bit long, but thanks for bearing with me, and that's all I got for you for now. So we'll see you next time. Thanks for watching.